So as introduced, I will be talking about modeling accretion shocks at the disk envelope interface. So to start with this quite familiar picture, which we've already seen quite a few times today. So I'll be very short on this, that I will be focusing in the star formation sequence on the embedded protostellar phase. And an important thing to note here is that we're really talking here about somewhat higher densities than typical molecular cloud phase, so at 10 to the 6, 10 to the 8 cubic centimeter. So zooming in on this picture, we have here this envelope disk system, basically. And what we have is that the envelope is actually falling onto this disk as it is, as the protostellar system is evolving. And there might actually or might not be an accretion shock at the disk envelope interface here. So one of the questions which arise from this here is actually whether there is such an accretion shock, because it is not being undisputedly proven. And the second question which follows up from that is the inheritance versus reset question, is how such a shock will alter the envelope material which enters the disk. And this is actually very relevant because we think that planets are forming in such a disk, and this is the material that eventually will feed these forming planets. So how this composition change is actually very relevant. However, I will not cover this second question in this talk, but I will solely focus on actually whether there is such an accretion shock or not. And that's actually where ALMA has become very useful due to its spatial resolution and sensitivity. So I'm showing here for an L1527, which is an edge-on disk. I'm showing in color the C4H2 emission, and then contours warm SO emission. So warm means here, say, 50 to 100 Kelvin. And what you actually see already is that we can spatially, these two species are spatially at different positions. And actually, if we always start looking at the kinematics, so drawing a position velocity diagram, we can actually see that the C4H2 here is tracing a rotating inner envelope, but the SO is doing something differently. And the authors suggested that this might be such an accretion shock. Well, similarly for SO2, we also, people have also observed warm SO2 in such embedded systems. So these are for 2 class 1 systems. Where the arrows denote the outflow direction, and the colors plot is actually the rotation signature of warm SO2 emission, which is seen to be perpendicular to this outflows. And also, when looking at the velocity profile, people they have suggested that this also might be originating from such an accretion shock. So warm SO and SO2 emission might actually be a good candidate for tracing these accretion shocks. However, there's a caveat there. Warm SO and SO2 emission is also seen in other places in protostellar systems. So, for example, on the left part, the author saw that it was in the warm inner envelope, actually, while it might also be located in the outflow directly for both SO and SO2 seen in the right picture. So from this, we can actually, we have to narrow down our question whether there is a strong accretion shock at disk envelope interface, to under what shock conditions the abundance of warm SO and SO2 in such shocks is increased. And to actually answer that question, we have to invoke modeling. So that's what I'll be talking about. So to very shortly introduce the concept of shocks, I will be talking here about so-called J-type shocks or jump shocks. And these occur in weakly magnetized environments. So what happens is that you have the shock front, and almost discontinuously you increase your gas temperature and density. And that is actually followed by the gas then cooling down, and due to the thermal coupling, the density increases while the gas is cooling down, and therefore you increase your density even more. And you can see here that actually the increase in density might be up to 2 orders of magnitude even. And another part which is very relevant to understand SO and SO2 accretion shocks is to understand the chemistry and sulfur chemistry in shocks. And here we have to make a distinction between gas phase chemistry and ice sublimation. So starting with the gas phase chemistry, a key species here is OH. And OH forms from molecular hydrogen with oxygen reaction. And this is an energy barrier of about 100 Kelvin. So in shocks, typical shocks, which typical shock I just showed you, this temperature is easily reached. And then if you have atomic sulfur in your gas, then you actually, this can react with OH to form SO, and then subsequently react with to SO2. So from this you would say, well, if your temperature is above about 100 Kelvin, you should have efficient gas phase formation for SO and SO2. But there's one big caveat here, and that's water. because the reaction for water starts at about 300 Kelvin, and that's from H2 with OH. And since H2 is so much more abundant than atomic sulfur, this reaction will immediately dominate. So following these equations, these reactions, you can suggest that between 100 and 300 Kelvin is about the right sweet spot of temperature for efficient gas phase formation of SO and SO2. So now moving on to the ice sublimation, that's a bit more straightforward. You just need to raise your dust temperature to the so-called sublimation temperature of an ice, so that it is released from the ice into the gas phase. And for SO, this is approximately 45 Kelvin-ish, and for SO2, this is about 60 Kelvin. So from that, you can conclude that we need about 45 Kelvin to have thermal ice sublimation. So moving now actually to our shock modeling. Like I said, the goal is to test SO and SO2 as traces of accretion shocks. And to do this, we use the Paris-Durham shock code, which is a shock code that has been developed over the past 30 years or so. But we're exploring an entire new parameter space. So we're really looking at shocks in very dense areas, so inner envelope, so typical densities 10 to the 6, 10 to the 8. Additional that we're talking actually about low velocity shocks, because the infalling envelope moves at few to max 10 kilometers per second. And another important thing is that we assume that our dust grains have grown in the envelope. So we don't have a typical ISM distribution anymore, but we, for simplicity, we assume here that they have all grown to 0.2 micron in size. And additionally to that, polycyclic aromatic hydrocarbons, or PAHs, are assumed to be frozen out on these dust grains. Hence, the abundance is about 2 orders of magnitude lower than in the ISM. And the latter point here is that I'm noting is that we actually test the effect of G0 in our modeling on the accretion shocks. So to put it in a physical picture, all models are run in as 1D models. So this is just a schematic. But we actually start with our so-called dark cloud conditions. So just mostly species are in the ices. But we assume that due to the last, say, 100 years of infall, our gas which is falling onto the disk is actually already being irradiated by the protostar. So we take this into account. And then following that, we actually calculate the shock model, which is shown in the bottom right here. So moving to our fiducial model, this is done for a typical density of 10 to the 7, an intermediate G0 of 1, and a low velocity shock, so 3 kilometers per second. And we can see the characteristic shock structure that I showed earlier. So we have here at the beginning of the shock, we have our increase in both gas temperature and also the dust temperature, followed by the gas and the dust cooling down. So it's already important to note here that our dust temperature in this model does not reach the ice sublimation. So any SO and SO2 which should form in the gas if we want to increase the abundance. But recall that this happens between 100 and 300 Kelvin. That's what we saw earlier. So where does it happen in this figure? It's really here on the tail, where the gas temperature drops to below 300 Kelvin and still above 100 Kelvin. So do we actually see this increase in SO and SO2 abundance here? Yes, we do see that. So in the shaded area, I'm showing here where the gas temperature is above 50 Kelvin, and we see that indeed towards the end and even a bit below the 50 Kelvin limit, our abundance of SO and SO2 is increasing, and this is actually due to the gas phase formations, which I just introduced. But of course, we're not only interested in the fiducial model, we want to test this for many physical conditions. So we run the shock models for many difficult physical conditions. We assume here a G0 of 1, and we test what is the effect of initial density and initial shock velocity. And to understand that, I first have to show you what is the effect on the temperatures. So starting with the maximum gas phase temperature reached in the shock, this is actually analytically, you can actually calculate this analytically from the equations which govern the shock, and it goes as the shock velocity squared. And that's also exactly what we see here. Is that it goes up, and it only depends on the velocity. The black square, by the way, is the fiducial model. However, the dust temperature depends on both density and input density and input velocity, and that's because the dust temperature depends on is calculated by the thermal coupling between dust and gas, and that's dependent on density. Well, how that works is, of course, if you start with a higher initial density, your dust is warmer, so that's pretty straightforward. But if you have a higher initial velocity, you actually compress your material more in your shock, hence you increase the density more. And that also results in an increase in dust temperature. So that results basically, and the most important thing to remember here is that the dust temperature moves up from bottom left to top right. So moving now to the species of interest, SO and SO2. For SO here on the right, I'm showing where the ice line is. So on the top right here, all the abundance of SO is dominated by ice sublimation because we assume that the abundance of SO ice is just higher than what we should form in the gas. So, but on the lower left here, we have this whole other regime, and that's actually where we do have this gas phase SO information in the tail of the shock. And for SO2, we actually see mostly a similar pattern. We see on the top right, it's a bit higher desorption temperature, so it's located a bit more on the top right. We see here the ice sublimation part, and on the bottom left, it's a bit less strong, but we still see formation way, gas phase formation way. But we have this other regime here, which is located just below the ice line, but which is hidden here in the as the SO is already desorbing. And that's actually here due to the H2S ice line. So what's happening here? Above in this regime here, the H2S is actually also sublimating, and due to the G0, so the G0 of 1, or the radiation field basically, due to the radiation field, this H2S is photodissociated into atomic sulfur. And therefore you increase your atomic sulfur abundance, and that enhances the reaction, or increases the reaction towards SO and SO2 formation. So that's really why we see this this other peak of gas phase formation, SO2 here. So as I said, this is dependent on G0 because you need to photodissociate it. So then we actually also want to test what is the effect of G0. And that's actually what I'm showing here. So the right figure here is the same as I just showed you, but in the left, I'm showing it for a lower G0 of 10-2. And we actually see that both gas phase formation waves for SO2 disappear, and a similar pattern is visible for SO. So this formation is apparently, besides temperature, also dependent on G0. And why is that? Why is that the case? Partially due to the photodissociation of H2S, what I just discussed, but also due to the photodissociation of water, because that will bring back even more SO or OH into the gas phase than just the reactions of H2 plus O, and therefore again increase the reactions into SO and SO2. So this G0 dependence is also not to be underestimated, and it's actually we found that between 0.1 and say 10-ish is really the sweet spot for SO and SO2 formation. So
you have 3 minutes.
Yes, so I'm actually finalized. To finalize, to tell you under what shock conditions, I was going to tell you under what shock conditions the abundance of warm SO2 is increased. Well, if we assume gas phase formation, we need a gas between 100 and 300 Kelvin, and we need a G0 of between 0.1 and 10. And we need either a rather low initial density, no initial shock velocity, or high initial density, high initial shock velocity. And for ice sublimation, we really need to go to the highest initial densities and initial shock velocities. And a last key takeaway message I want to make is that sometimes a year of advanced modeling can be necessary to start understanding ALMA data. So ALMA data on itself are really beautiful and really nice, but sometimes it can take some time to start understanding them. Thank you.